Hello and welcome to the Analog Devices Precision Training video that focuses on precision digital-to-analog converter technology. This video will go through the architectures associated with digital-to-analog converters, or DACs. We will discuss the key differences between these type of DAC architectures, and we will highlight the advantages that each architecture has to offer for your design. A DAC is used to convert a digital input signal into an analog output signal. The digital signal is set by a binary code that is a combination of ones and zeros. A simple DAC can be easily implemented using a binary-weighted network. The current, I, is the sum of the individual currents flowing through the input resistors. Here we show a 3-bit DAC, which can easily be expanded to an n-bit DAC by increasing the number of resistors used to n. Some key challenges associated with this type of DAC are achieving and maintaining accurate performance and excellent monotonicity, due to the resistors needing to be matched and the ratios tightly controlled. The simplest DAC architecture structure of all is the Kelvin divider, or string DAC. An n-bit version of this DAC simply consists of 2 to the n equal resistors in series, and 2 to the n switches, each one located between each node of the chain and the output. A key advantage is the monotonicity associated with this architecture. However, a large number of components are required to implement such a DAC, making it non-practical architecture if high resolution is required. If we now look at a voltage segment DAC, here the number of resistors required is much less. This design uses 2 chains of 2 to the n resistors, where the second string of resistors are connected across adjacent taps on the main string. The voltage between the 2 taps is further subdivided, leading to an increase in the resolution. A number of buffers exist between the first and second stage. This enables the removal of the loading between the 2 strings, allowing resistor value in each string to be different. Resistor string DACs are monotonic by design. Additional benefits include simplicity, higher density, and low power consumption. Key considerations. The output impedance is relatively high at mid-codes, thus an output buffer is required to minimize load effects. The higher output impedance has an effect on the thermal noise. This is higher when compared with other DAC implementations discussed. If we now look at the new string architecture associated with DACs, this overcomes the shortcomings of the previous architectures, where the substring needed to be either buffered or had to be of a much higher impedance to remove the loading effects. For this new architecture, the error sources are reduced further through the incorporation of the second string in the overall transfer function. This string appears in parallel with the resistor in the main string. This leads to a voltage drop across that main string resistor by 1 lsb of the second string, and is exactly what is required. The main string consists of 2 to the n over 2 resistors, and the second string consists of 2 to the n over 2 minus 1 resistors. A key requirement is that the resistors in the 2 strings must be equal, apart from the top resistor in the MSB position. This is used to reduce gain error effects. This DAC architecture ensures guaranteed monotonic, high-resolution, low constant power voltage output DACs. Analog Devices has many different types of precision string DACs, from varying resolution, channel count, wide range of operating voltage and temperature ranges, to many different packaging and digital interface options that are applicable to many different applications. To learn more about additional DAC architectures, specifications, and applicable applications, please continue to watch our next video in the DAC Precision Training series. Click on the link below or go to Analog Devices Precision Digital to Analog Converter landing page.